The story of modern physics is one of daring simplicity, hiding behind complex mathematics. For centuries, humanity believed the rules that govern nature could be reduced to a handful of principles, and remarkably, this turned out to be true. Yet when we examine the framework that defines our understanding today, we find not just clarity, but also deep mysteries. These mysteries whisper of the possibility that our universe, with its particular balance of particles and forces, might not be the only way reality can be arranged. To appreciate this puzzle, we must first trace the scaffolding of physical law, as it is known now. The standard model of particle physics is the central pillar of this framework. It tells us that the familiar atoms of the world are not fundamental. Atoms are made of protons, neutrons, and electrons, but even these are not the end of the story. Protons and neutrons are themselves made of quarks, particles bound tightly by the strong nuclear force. Quarks come in 6 varieties, or flavors, with names that sound whimsical but represent rigorous categories: up, down, strange, charm, bottom, and top. Alongside quarks are leptons, which include the electron, its heavier cousins, the muon and the tau, and a family of ghost-like neutrinos. These particles are the building blocks of matter. Matter alone would remain mute without forces, and the standard model gives us those too. The electromagnetic force binds atoms together and allows light to travel across space. The strong nuclear force glues quarks into protons and neutrons and keeps atomic nuclei intact. The weak nuclear force allows particles to transform, powering processes such as the fusion reactions in the core of the Sun that make life possible on Earth. Each of these forces has its carrier particles, which are the messengers of interaction. Photons carry the electromagnetic force, gluons carry the strong force, W and Z bosons carry the weak force. Together, this ensemble of matter particles and force carriers accounts for almost everything that happens in the visible universe. But one crucial element was missing until fairly recently. Without a mechanism to explain why particles have mass, the equations of the standard model remained incomplete. This missing piece arrived with the Higgs field, an invisible energy field that permeates all of space. Particles acquire mass through their interaction with this field. The associated quantum excitation is the Higgs boson, whose discovery in 2012 at the Large Hadron Collider in Geneva was hailed as a crowning triumph of modern science. This was not simply the confirmation of a theory, but the completion of an edifice that had been built brick by brick over decades. Yet the standard model is not the whole picture. While it unites 3 of the 4 known forces of nature, it leaves out gravity, the most familiar force of all. For that, we turn to Albert Einstein and his general theory of relativity. In the early 20th century, Einstein shattered the Newtonian view of gravity as a force acting at a distance. Instead, he revealed that space and time are woven together into a single fabric, space-time, which can bend and curve. Massive objects such as stars and planets do not pull on one another by some invisible tether. Rather, they create dents in the fabric of space-time, and other objects move along the curved paths this geometry dictates. The predictive power of this theory is extraordinary. It explained the small but persistent anomaly in Mercury's orbit that Newton's equations could not account for. It forecast the bending of starlight by the gravity of the Sun, a phenomenon observed during a solar eclipse in 1919, a moment that catapulted Einstein to worldwide fame. In the past decade, general relativity passed yet another test of breathtaking precision when the Laser Interferometer Gravitational Wave Observatory detected ripples in spacetime from colliding black holes. These waves traveled for more than 1 billion years before reaching Earth, yet their signal matched the predictions of Einstein's equations almost perfectly. Thus, we have 2 grand frameworks: the standard model for the very small and general relativity for the very large. Both are astonishingly successful, and both rely on certain constants of nature that appear fixed and unchanging. Among the most fundamental are the speed of light in a vacuum, denoted by the letter c, Planck's constant h, that sets the scale of quantum uncertainty, and Newton's gravitational constant g, that governs the strength of gravity. There is also the fine structure constant, often called alpha, which determines the strength of electromagnetic interactions. These constants are not derived from deeper principles. They are measured in experiments, written into the equations, and then everything else follows. The precision with which these laws have been tested is nothing short of extraordinary. At particle accelerators, beams of protons collide at speeds close to that of light, recreating conditions of the early universe. Detectors capture the fleeting showers of particles, and the results conform again and again to the expectations of the Standard Model. In gravitational physics, observatories on Earth and telescopes in space trace the faint distortions of space-time itself, revealing that Einstein's equations hold true across scales, ranging from planetary systems to colliding galaxies. The framework is not only coherent, but also durable under the most extreme scrutiny. And yet, for all this triumph, the framework raises a deeper puzzle. Why these laws? Why these constants? Why should the electron have precisely its measured mass, or the strength of gravity be so weak compared to the other forces? The framework of modern physics does not answer such questions. It accepts the constants as given, writes them into the equations, and proceeds. But their very existence as arbitrary numbers tempts us to wonder whether they are necessary features of reality or merely contingent facts of this particular universe. That is where the journey ahead takes us. These laws hold with astonishing precision, but the deeper question of why they hold as they do remains unanswered. The search for deeper order has always driven physics. Each generation of scientists has asked whether the constants and rules we see are necessary, or if they can be explained by something more fundamental. This search is not new. In the 19th century, James Clerk Maxwell showed that electricity and magnetism were two aspects of the same force, uniting them in a set of equations that still stand as some of the most elegant in science. In the 20th century, physicists extended this unification, showing that electromagnetism and the weak nuclear force are two faces of a single electroweak interaction. The discovery of the Higgs boson confirmed this vision. The question naturally arises, can the strong force and gravity be included too, bringing all of nature under one mathematical roof? The attempt to unify all forces has met with both progress and frustration. Quantum field theory provides a language in which particles and forces are described by vibrating fields that permeate space. The mathematics of these fields is astonishingly precise, allowing predictions that agree with experiment to many decimal places. Yet when gravity is placed into this framework, contradictions appear. Gravity resists being quantized in the same way as the other forces. This tension points to the incompleteness of the current framework and hints at a deeper level of structure waiting to be uncovered. Amid these mysteries, the role of symmetries has proven crucial. In physics, symmetry does not mean simple beauty of shape, but rather invariance under transformation. If a system behaves the same when shifted in space, that is a spatial symmetry. If it behaves the same when shifted in time, that is a temporal symmetry. Emmy Noether, one of the greatest mathematical minds of the 20th century, proved a theorem that has become a cornerstone of theoretical physics. She showed that every continuous symmetry corresponds to a conservation law. Invariance under time translation implies conservation of energy. Invariance under spatial translation implies conservation of momentum. Invariance under rotation implies conservation of angular momentum. The laws of physics are thus deeply tied to the symmetries of the universe. The Standard Model itself is built upon a rich network of symmetries, known in the technical language of physics as gauge symmetries. These symmetries dictate the kinds of interactions that can exist and forbid others. They also explain why the particles we observe have the charges they do. In this sense, symmetries act like scaffolding, holding the structure of physics in place. Break those symmetries, and the laws of physics themselves would look profoundly different. Experiments across the globe continue to test these principles with exquisite precision. In Japan, neutrino detectors buried deep underground capture faint flashes of light from elusive particles passing through Earth, testing the limits of the Standard Model. In Switzerland, the Large Hadron Collider smashes protons together at energies that push human engineering to the edge, searching for cracks in the Standard Model's predictions. In the United States, gravitational wave observatories stretch laser beams along kilometers of vacuum-sealed tunnels, waiting for the faint tremors of space-time that mark the distant collision of massive objects. Each result so far has only reinforced the extraordinary accuracy of our current framework. Yet every confirmation is also a reminder of the unsolved puzzles. Dark matter, which outweighs visible matter by a factor of about 5, remains invisible to the standard model. Dark energy, which drives the accelerated expansion of the cosmos, is completely unexplained within it. Even the Higgs boson, triumphant as its discovery was, raises new puzzles about why its mass is what it is and why it does not destabilize the entire theory. The framework of modern physics, for all its power, feels like a provisional structure, as if nature has given us the front hallway of a vast palace, but keeps the inner chambers hidden. The constants that define the framework intensify the mystery. Take the fine structure, constant, alpha. It is a dimensionless number, roughly 1 divided by 137, that determines the strength of electromagnetic interactions. If alpha were even slightly different, the chemistry of atoms would not work in the same way. The bonds that make molecules stable, the energy levels that give rise to spectra of light, even the reactions in stars that forge elements, all depend on this delicate number. But why should alpha have this value and not another? Physics as we know it has no answer. Or consider Newton's gravitational constant, g. Gravity is by far the weakest of the known forces. A simple refrigerator magnet can lift a paperclip against the gravitational pull of the entire Earth. If gravity were much stronger, stars would burn out in a fraction of their current lifetimes. If it were much weaker, galaxies might never form. The framework of physics accepts the value of g as a given, but the fact that it falls within a narrow life-permitting range has led many scientists to ponder its deeper significance. Planck's constant, h, sets the scale at which quantum effects appear. Without it, the entire quantum world would collapse into classical predictability. Its value ensures that atoms do not collapse, that electrons form shells, and that chemistry is possible. Again, the framework accepts it without explanation. It is written into the equations, measured in laboratories, and taken as one of the pillars of modern science. These constants, scattered through the edifice of physics, give the universe its particular flavor. They make it the way it is, and not some other way. The framework of modern physics describes them, uses them, and builds upon them, but it does not reveal why they are what they are. That question lies beyond the current horizon. The deeper we study the framework, the more we see that it is both complete and incomplete. Complete, in that it accounts for almost every experiment we can devise. Incomplete, in that it leaves fundamental questions untouched. Why these particles? Why these forces? Why these constants? These are not trivial curiosities, but questions at the heart of understanding reality itself. The framework of modern physics is therefore a paradoxical triumph. It is the most accurate, predictive, and powerful body of knowledge humanity has ever built about nature. Yet its very success draws attention to what it cannot explain. It describes, but does not justify. It reveals, but also conceals. It gives us the universe as it is, but not why it is so. This tension is what propels science forward. Physicists look at the constants, the symmetries, the successes, and the gaps, and they ask whether there might be other frameworks, perhaps in other universes, where the rules are written differently. When we speak of laws of physics, we must be clear about what we mean. They are not commandments written into the fabric of reality, but human descriptions of patterns we observe with remarkable regularity. They are distilled from experiments, codified in equations, and tested in prediction after prediction. Their universality lies in their survival against challenge. Drop a ball in Tokyo or in Buenos Aires, and it falls to the ground with the same acceleration. Fire a beam of electrons in Geneva or in California, and they bend in magnetic fields in exactly the same way. The laws hold across place and time, as far as we have tested. This reliability is the reason we dare to call them laws. Still, history teaches caution. For centuries, Newton's laws of motion and his universal gravitation were believed to be eternal truths. They worked flawlessly for everyday motions on Earth and even for the orbits of the planets. Yet they broke down at extreme speeds, extreme masses, and extreme scales. Einstein showed that Newton's framework was only an approximation, an elegant but limited lens on reality. It is entirely possible that what we now call the Standard Model and general relativity are similarly approximations, accurate to extraordinary precision in their domains, but destined to give way to deeper frameworks under more extreme conditions. Those conditions existed in the earliest moments of the universe. In the first fraction of a second after the Big Bang, energies were so immense that the familiar distinctions between forces may not have existed. The electroweak force had not yet separated into electromagnetic and weak nuclear interactions. Perhaps even the strong force was united with them. Gravity, too, may have joined the dance. If such unification occurred, it would mean that the laws we know are the cooled and broken remnants of a more symmetric and unified law. What we see today would then be contingent, the product of cosmic history, rather than eternal necessity. Experiments seek hints of this unification. Proton decay, if ever observed, would point to grand unified theories where quarks can transform into leptons. Supersymmetry, a proposed extension of the Standard Model, predicts a hidden partner particle for each known particle, a symmetry that could stabilize the Higgs boson's mass and perhaps explain dark matter. So far, no such evidence has emerged, but the search continues. Each null result sharpens our picture of the framework, ruling out some possibilities and guiding us toward others. At the same time, cosmology probes the large-scale structure of the universe, testing general relativity across cosmic expanses. The observation of accelerating cosmic expansion, attributed to dark energy, strains our understanding. Einstein's equations can accommodate it with a cosmological constant, but the measured value is stunningly small compared to naive predictions from quantum field theory. This discrepancy remains one of the deepest unsolved puzzles of modern physics. The framework allows us to describe the effect, but not to explain its magnitude. Thus, in both the microcosm of particles and the macrocosm of galaxies, the framework of modern physics shines and falters. It gives us tools of unparalleled precision, yet leaves us facing questions it cannot answer. The constants that define it seem arbitrary. The symmetries that support it seem contingent. The forces it describes may be fragments of a deeper unity. Its very triumph is to reveal its own limitations. The framework is not merely a set of equations on paper. It is embodied in the instruments we build, the technologies we rely on, the very infrastructure of modern life. Semiconductors, lasers, medical imaging, GPS satellites all depend on the truths revealed by quantum mechanics and relativity. The fact that these laws work so well in our devices reinforces our confidence in their power. And yet, even as they enrich our lives, they provoke the intellectual unease that they may be provisional. This unease is the seed of our inquiry. If the laws of physics are not ultimate, then perhaps they could have been different. If they could have been different, perhaps they are different elsewhere. Perhaps other universes exist where constants take other values, where symmetries break in other ways, where matter and energy organize into structures utterly unlike our own. Such speculation is not idle fantasy. It is compelled by the very questions the framework cannot answer. The framework of modern physics is thus both a foundation and a launching pad. It grounds us in reliable knowledge, while pointing beyond itself to mysteries still unsolved. It gives us extraordinary predictive power, while reminding us of the limits of human understanding. And it opens the door to the central question of this journey. Are these laws universal, or are they merely one chapter in a much larger story of reality? With this question in mind, we step forward, leaving the secure ground of established frameworks to confront the puzzle of fine-tuning, the enigma of why the laws and constants have the precise values they do, and what that might mean for the possibility of other universes. The framework of physics reveals astonishing precision, but it also confronts us with unsettling questions. When we measure the constants of nature, we find that they are not arbitrary in their effects. small changes in their values would make the universe profoundly different, often in ways that seem hostile to the possibility of complex structures, chemistry, and life. This peculiar sensitivity is what scientists call fine-tuning. It is one of the most thought-provoking enigmas in modern physics, not because it points to supernatural design, but because it raises the possibility that the laws we see might be contingent. If the constants were different, the universe might be lifeless. And yet here we are, in a universe where the conditions line up with remarkable precision to permit our existence. One of the clearest examples of fine-tuning comes from the story of carbon. Carbon is the backbone of life. It forms the chains and rings that build the molecules of biology, from proteins to DNA. But carbon itself is forged in the hearts of stars through a delicate nuclear reaction. When helium nuclei, called alpha particles, fuse in stellar cores, they can form beryllium. Beryllium is unstable and decays almost instantly. But if another helium nucleus collides at just the right moment, the fusion can produce carbon. For this process to be efficient, there must be a resonance, an energy level in the carbon nucleus that matches the combined energy of the incoming particles. In the 1950s, the astrophysicist Fred Hoyle predicted such a resonance must exist, even though it had never been observed. His prediction was later confirmed. Without this specific energy level, the stars would produce far less carbon, and the chemistry of life might never have emerged. The fact that this resonance falls precisely where it needs to be is often cited as an example of fine-tuning. Another striking case comes from the balance of forces. Electromagnetism and gravity differ in strength by a staggering margin. The electromagnetic force is roughly 10 to the power of 36 times stronger than gravity. This disparity is what allows stars like our Sun to shine steadily for billions of years rather than collapsing or burning out in an instant. If gravity were only slightly stronger relative to electromagnetism, stars would fuse their fuel too quickly, living short and violent lives. If gravity were weaker, gas clouds might never compress enough to ignite nuclear fusion, and stars would never form at all. The very fact that we have a stable star providing warmth and light on a planet where chemistry can flourish is tied to this delicate balance between two forces whose relative strengths seem unrelated, yet fall into a life-permitting range. The puzzle deepens with the cosmological constant, the term in Einstein's equations that represents the energy density of empty space. In quantum field theory, the vacuum is not truly empty, but seethes with virtual particles and fields. Calculations suggest this energy should be enormous, yet observations of cosmic acceleration show it to be extraordinarily small. The difference between the theoretical expectation and the measured value is on the order of 120 powers of 10. This mismatch is often described as the worst prediction in physics. More profoundly, if the cosmological constant were much larger than observed, the universe would have expanded so rapidly after the Big Bang that galaxies and stars could never form. If it were much smaller, the universe might have collapsed back on itself long ago. The fact that it sits within a narrow range that allows billions of years of cosmic evolution is another case of apparent fine-tuning. Such examples make it tempting to see purpose or design, but science takes a different approach. Physicists analyze these coincidences with caution, recognizing that human existence selects for certain conditions. This perspective is called the anthropic principle. It states, at its most basic, that we should not be surprised to observe a universe compatible with life, because otherwise we would not be here to ask the question. This reasoning does not explain the values of the constants, but it reframes the puzzle. Perhaps many values are possible, and we find ourselves in a region of possibility where conditions are right for us. The anthropic principle comes in weaker and stronger forms. The weak version is almost tautological, reminding us that our observations are biased by our existence. The stronger version speculates that the universe must be structured in a way that permits observers, which drifts toward philosophy. Scientists generally accept the weak form as a caution against misinterpretation, but the stronger form remains controversial. Still, the anthropic idea provides one way to interpret fine-tuning without invoking necessity or design. Whether or not one embraces anthropic reasoning the fact remains that the constants of physics lie in ranges that allow complexity and life. This delicate arrangement compels us to ask, are these values inevitable or contingent? Could they have been otherwise? If so, what determines them? The puzzle of fine-tuning presses against the boundaries of science, forcing us to confront the possibility that our universe is not the only one, or that deeper laws exist which select the constants we observe. The question cannot be ignored, for it cuts to the heart of physics itself. If the laws are necessary, then they may be uniquely determined by logic and mathematics. If they are contingent, then perhaps there are other ways reality could have been arranged. Either answer would reshape our understanding of what it means for a law to be a law. The more deeply we study the constants, the more precarious their balance appears. Take the strong nuclear force, the binding agent of protons and neutrons inside atomic nuclei. If the strength of this force were only a few percent weaker, atomic nuclei would not hold together beyond hydrogen. The universe would contain no carbon, oxygen, or heavier elements. Chemistry would be reduced to the simplest structures, barren of complexity. If the strong force were only a few percent stronger, hydrogen itself might vanish as protons and neutrons fuse too readily, leaving no fuel for stars like our Sunday. Either way, life as we know it would be impossible. The weak nuclear force also plays a crucial role in shaping the universe. It governs radioactive decay and enables the sun to shine by allowing protons to convert into neutrons in the fusion process. If the weak force were much weaker, the chain of reactions in stars would grind to a halt, and the cosmos would be cold and dark. If it were much stronger, stars might burn their fuel too quickly, never achieving the long, stable lifetimes necessary for life to evolve. The weak force, though often overshadowed by its more famous siblings, is thus finely poised in its strength. Even the ratio of masses between fundamental particles reveals fine-tuning. The proton is about 1,836 times more massive than the electron. This imbalance allows atoms to form in which electrons orbit light enough to be influenced by protons, yet heavy enough to avoid being flung away by quantum fluctuations. If the electron were much heavier, atoms would collapse into unstable forms. If it were much lighter, chemical bonds might fail to stabilize. Once again, the values appear delicately arranged. Cosmic scales reveal the same pattern. The density of matter in the universe, measured against the rate of cosmic expansion, lies in a narrow window that permits galaxies and stars to form. If the density were much higher, the universe might have collapsed long ago. If much lower, matter would have dispersed too thinly to clump into galaxies. Similarly, the initial conditions of the Big Bang had to be remarkably uniform, with temperature variations across the early cosmos of less than 1 part in 100,000. This uniformity seeded the cosmic structures we see today, but its precision defies simple explanation. The sense of improbability grows when we realize how many factors must align at once. It is not only one constant or one force that matters, but the entire ensemble working together. Stars must form and shine steadily. Heavy elements must be produced and dispersed. Planets must condense in stable orbits, and chemistry must flourish. Each step depends on a network of finely balanced parameters. The odds of all of them lining up by chance seem vanishingly small. This impression of unlikeliness has led some thinkers to propose that perhaps we should not view our universe as uniquely determined. Instead, they suggest that many universes may exist, each with different constants. In such a vast ensemble, most universes would be sterile, but a tiny fraction would fall into the narrow ranges that permit life. The fact that we find ourselves in one of these rare universes would then require no further explanation. It would be an inevitable consequence of probability and observation. Yet not all physicists are comfortable with this line of thought. The multiverse idea, while offering a possible resolution to fine-tuning, is difficult to test directly. Science thrives on falsifiability, the ability to prove or disprove a claim through observation. If other universes cannot be observed, does the concept belong to science at all? Some argue that it does, if indirect predictions or consistency with established theories can be shown. Others argue that it strays too close to metaphysics, Still, fine-tuning is not easily dismissed. Even without invoking a multiverse, the puzzle demands attention. Some hope that deeper physical principles will one day show that the constants are not arbitrary but necessary. Perhaps mathematics itself constrains them to their values, just as the ratio of a circle's circumference to its diameter must be pi. In this view, fine-tuning would dissolve once the underlying theory is revealed. The question remains open. What is clear is that the constants, as we measure them, seem uncannily well suited for complexity. The impression of fine-tuning is real, even if its ultimate explanation remains elusive. The recognition of fine-tuning has reshaped the way scientists think about the laws of physics. For centuries, the assumption was that the laws were necessary, unique, and absolute. They were seen as the bedrock upon which the universe was built, fixed and unchangeable. But the discovery that small variations in the constants could make the universe sterile introduces a new possibility. Perhaps the laws are not uniquely determined. Perhaps they are contingent, arising from conditions that could have been otherwise. This shift is not easy for science to embrace. Physics has long sought universal principles that hold everywhere and everywhen. The idea that laws might differ across regions of reality seems unsettling. Yet the puzzle of fine-tuning forces us to consider it seriously. If the constants are contingent, then either they were selected by some unknown mechanism, or they exist in many versions across a vast landscape of possibilities. The anthropic principle remains a central part of the debate. It does not solve the puzzle, but it reframes it. Instead of asking why the constants permit life, we recognize that only life-compatible values could ever be observed by beings like us. Still, this reasoning leaves the deeper question untouched. Why is there a range of possible values at all? Why does the universe allow for life in any form, rather than none? Some scientists point to the role of symmetry breaking in the early universe. The laws we observe today may have emerged from transitions in which underlying symmetries shattered, leaving behind specific values for constants. In this picture, the constants are like the properties of ice compared to water. Both phases arise from the same underlying substance, but their forms differ because of conditions. If our universe is the result of one particular symmetry breaking, then others might be possible, each giving rise to different laws. Others turn to mathematics itself for answers. They wonder whether there exists a deeper principle that forces the constants to take the values they do. In this vision, fine-tuning is an illusion, a sign that we have not yet uncovered the final theory. Just as earlier puzzles dissolved with the discovery of new frameworks, perhaps fine-tuning will vanish when the true unifying laws are found. The debate touches not only on physics but also on philosophy. It raises questions about explanation, necessity, and chance. It invites us to reconsider what it means for a law to be fundamental. Are the constants simply brute facts, beyond explanation? Are they the result of cosmic lottery, with our universe as one lucky outcome among many? Or are they dictated by a deeper logic that we have not yet glimpsed? For now, we do not know. But the puzzle of fine-tuning is more than a curiosity. It is a beacon pointing beyond the current framework, urging us to seek new principles, new theories, or perhaps even new ways of thinking about reality itself. It reminds us that the universe is not only comprehensible but also strangely poised, balanced on a knife edge that permits complexity and life. As we follow this thread, we move from the recognition of fine-tuning to the question of whether the constants can vary. Are they fixed everywhere and for all time, or might they shift across space and history? To explore this, we turn to the next chapter, where experiments test whether the laws we take as unchanging might in fact show subtle signs of variation. The puzzle of fine-tuning leads naturally to the next question. If the constants of nature seem finely adjusted, are they fixed forever, or might they shift with time and place? For centuries, the assumption was that they were immutable. The speed of light, the strength of gravity, the ratios of particle masses, all were taken as eternal features of reality. But science advances by testing assumptions, and in the past century, physicists have devised increasingly precise experiments to see whether the constants truly remain constant. The first candidate for variation is one of the most famous numbers in physics, the fine structure constant. This dimensionless constant, roughly 1 divided by 137, sets the strength of electromagnetic interactions. It governs how electrons orbit atomic nuclei, how atoms emit and absorb light, and how chemical bonds hold molecules together. If alpha were different, atomic spectra would shift, chemistry would be altered, and the light from distant stars would carry a different fingerprint. This makes it an ideal constant to test for variation across cosmic distances. In the late 20th century, astronomers began examining the light from quasars, brilliant beacons powered by supermassive black holes in the early universe. As light from these quasars passes through clouds of gas on its journey to Earth, the atoms in those clouds absorb certain wavelengths. By studying these absorption lines, scientists can measure the value of the fine structure constant billions of years in the past. Some studies, particularly those led by John Webb and his collaborators, reported small deviations suggesting that alpha might have been slightly different in distant regions of the cosmos. The results hinted at a spatial gradient, as if the constant varied depending on direction in the sky. These findings stirred great excitement, but also skepticism. Other groups, analyzing different sets of quasar data, found no evidence of variation. The challenge lies in the complexity of the measurements. Spectrographs must be calibrated with exquisite precision, and even tiny instrumental shifts can mimic changes in alpha. As technology improved, instruments such as the Very Large Telescope in Chile and the Keck Observatory in Hawaii provided better data. The debate remains unresolved. Some analyses suggest tantalizing hints of variation, while others insist that the fine structure constant is constant to within experimental error. Laboratories on Earth provide another approach. By comparing atomic clocks that rely on different transitions, scientists can test whether the ratios of frequencies remain fixed over time. These clocks are astonishingly accurate, drifting by less than a second over billions of years. If the constants were shifting, the ticking of one clock compared to another would gradually drift. So far, no such drift has been detected, with limits on variation reaching parts in 10 to the power of 17 per year. This level of stability is extraordinary, suggesting that if constants vary at all, they do so at rates far smaller than anything yet observed. The proton-to-electron mass ratio offers another test. This ratio, about 1,836, determines the structure of molecules and the spacing of spectral lines. Astronomers have measured this ratio in distant gas clouds by analyzing molecular hydrogen lines in quasar spectra. Again, the results are mixed. Some claim slight variations over billions of years, while others see no evidence. Laboratory measurements using molecular transitions and precision spectroscopy also find the ratio stable to within remarkable limits. Despite the lack of definitive evidence, the pursuit continues because the stakes are high. If constants vary, even minutely, it would signal physics beyond the current framework. It would suggest that what we call constants are not absolute but emergent properties of deeper fields or processes. Such a discovery would revolutionize our understanding of physical law. The search for variation is not confined to astronomy and atomic physics. Geophysics provides another window. The natural nuclear reactor that once operated at Oklo in Gabon 2 billion years ago leaves behind isotopic ratios that can be compared to today's values. Analysis shows that nuclear reaction rates then were almost identical to now, placing strict limits on possible shifts in fundamental constants over geological time. This natural experiment, written into the rocks of Earth, reinforces the impression of stability. Still, the possibility remains. Our measurements are finite, our reach limited. What appears constant across the regions we can probe might differ beyond them. The question remains open. Are the constants truly universal, or do they reveal subtle variation when seen on scales grander than our own? The possibility that the constants might vary has consequences far beyond the technical details of spectroscopy or atomic clocks. It would reshape our very concept of what a law of nature is. If a constant, such as the fine structure constant, alpha, were to drift with time or differ across space, then the laws of physics would not be fixed universal truths, but context-dependent rules. They would resemble the weather, varying with conditions, rather than eternal commandments. This possibility, though unsettling, is precisely why scientists pursue the question with such care. The motivation is not only philosophical. Theoretical physics suggests reasons why constants might vary. In some versions of grand unified theories, the strengths of the forces are not truly constant, but run with energy scale. At higher energies, the coupling constants of the electromagnetic, weak, and strong forces evolve, and in some models, they converge at a unification point. If the values depend on underlying fields that themselves might shift, then small variations could leak into the constants we measure. Similarly, in string theory, the shapes and sizes of extra dimensions determine the values of physical constants. If these dimensions change, even subtly, the constants could change too. Testing for variation is thus a way to probe the deep structure of reality. If constants are perfectly stable, that constrains theories of unification. If they vary, it would point the way toward new physics. Either outcome is valuable. The challenge is that the expected variations, if they exist, are incredibly small, demanding measurements of extraordinary precision. Atomic clocks represent one of the most sensitive tools in this quest. Modern optical lattice clocks trap thousands of atoms in webs of laser light, allowing frequencies to be measured with astonishing accuracy. By comparing different species of atoms, such as ytterbium and strontium, scientists can detect relative shifts that would signal changes in constants. These experiments are now sensitive enough to detect variations at levels of 1 part in 10 to the power of 18 per year. So far, no changes have been seen. But the fact that we can test the stability of the laws of nature to such precision is itself remarkable. Astrophysical observations extend the reach of these tests across cosmic time. When light from quasars reaches us, it carries information from billions of years ago. If the constants had different values then, the absorption lines imprinted on that light would betray it. The same is true for the cosmic microwave background, the afterglow of the Big Bang, which encodes the physics of the universe when it was only about 380,000 years old. Analysis of the cosmic microwave background places limits on the variation of constants during that epoch, again showing remarkable stability. Yet even stability is informative. If the constants are stable, then they are not emergent from easily shifting fields, or those fields must themselves be locked in place. This narrows the possibilities for unification theories. For example, models in which a rolling scalar field alters constants over time must be tuned to avoid contradicting the tight experimental limits. In this way, the absence of evidence is not empty. It is data that sharpens the contours of theoretical speculation. There is also the intriguing possibility that variation might not be smooth but patchy. If the universe is larger than our observable horizon, different regions might have settled into different values during early symmetry breaking. Our region would then appear uniform, but other domains, unreachable to us, could follow different rules. Evidence for this is hard to find, but the suggestion fuels ongoing research into anisotropies in cosmic data. The search for varying constants has another dimension. It forces us to rethink how we define measurement itself. Constants such as the speed of light are embedded in our units of measurement. Since 1983, the meter has been defined by the distance light travels in a fraction of a second, making the speed of light fixed by definition. In this sense, variation must be sought not in absolute values, but in dimensionless ratios, such as the fine structure constant, or the proton to electron mass ratio. These ratios are the true carriers of physical meaning, independent of human conventions. So far, the universe has whispered only of stability. The constants, as far as we can tell, are constant, but the tests are still young. Instruments grow sharper each year, telescopes peer deeper into cosmic time, and laboratories refine the art of precision measurement. The question remains alive: will the constants hold forever, or will nature one day reveal that even its most trusted numbers are subject to change? The pursuit of varying constants embodies the spirit of science at its best. It takes nothing for granted, not even the stability of the rules that seem most fundamental. The fact that we can test these possibilities with instruments built by human hands is a measure of how far physics has come, from cave paintings and the first calendars carved in stone to atomic clocks that measure time with unimaginable accuracy. The journey reflects humanity's relentless drive to probe the structure of reality. The evidence so far points to remarkable stability. Across laboratory experiments, geological records, astrophysical observations, and cosmological data, the constants appear fixed to within astonishing limits. The fine structure constant is stable to at least 1 part in 10 to the power of 17 per year. The proton-to-electron mass ratio is stable to similar levels. Nuclear reactions 2 billion years ago produced results almost identical to those today. Light from quasars, billions of years old, carries absorption lines that, within measurement error, match the same constants we use in modern laboratories. But the absence of confirmed variation does not settle the puzzle. It leaves open 2 possibilities. One is that the constants truly are absolute, woven into the very fabric of mathematics and nature, unchanging for all time. The other is that they may vary, but at levels too subtle or too distant for our current reach to detect. Both possibilities matter. If they are absolute, we must ask why these values, and not others. If they vary, we must uncover the deeper framework that explains how and why. The idea of variation also connects directly to the concept of multiple universes. If constants can vary with space and time, perhaps they take different values in regions of reality beyond our horizon. Our universe might then be one patch in a larger mosaic, each patch defined by its own constants. The stability we observe locally could be just one slice of a greater diversity. In this way, the search for varying constants bridges the gap between empirical science and the speculative idea of a multiverse. The philosophical implications are profound. If constants can change, then the laws of physics are not eternal truths, but evolving features of the cosmos. They would resemble biological traits, shaped by conditions, rather than timeless axioms. If they do not change, then they stand as brute facts, leaving us to wonder why they are as they are. In either case, the puzzle presses us to think more deeply about the nature of law itself. The search continues with ever greater precision. New generations of telescopes, equipped with spectrographs calibrated to unprecedented accuracy, will test quasar light with more rigor than ever before. Next-generation atomic clocks, synchronized across continents, will push sensitivity beyond 1 part in 10 to the power of 18. Space missions may carry such clocks into orbit, testing whether gravity subtly alters the ticking in ways that reveal hidden variation. The coming decades will bring sharper answers, though whether they reveal constancy or change, we cannot yet know. For now, the lesson is one of humility. The constants appear fixed, but the universe has surprised us before. The discovery of cosmic acceleration, the detection of gravitational waves, the unveiling of the Higgs boson, all were once unimagined. To assume we already know the full story of the constants would be premature. Science advances not by certainty, but by doubt, by testing even the assumptions we trust most deeply. As we leave this chapter, the question remains alive. Are the constants truly eternal, or do they whisper of deeper structures that shift and evolve? To probe this, we must turn to the early universe, to the primordial moments when the laws themselves first emerged from a sea of raw energy. Only by studying those beginnings can we begin to understand whether the rules we know are universal necessities or historical accidents. To understand whether the laws of physics are fixed or contingent, we must turn our gaze to the earliest moments of the cosmos. For it was in those first instants after the Big Bang that the conditions of the universe were set, and with them, the framework of particles, forces, and constants that we live with today. By studying the early universe, we can glimpse not only how our laws came to be, but also whether they could have been different. The Big Bang theory tells us that the universe began about 13.8 billion years ago in a state of incredible density and temperature. In those first fractions of a second, the cosmos was a seething plasma of energy, too hot for atoms, protons, or even quarks to exist as bound states. The familiar structures of matter were absent. Instead, the universe was a storm of fundamental fields, a cauldron in which the eventual laws of physics were still being forged. As the universe expanded, it cooled. With cooling came order. Quarks bound together into protons and neutrons within the first microseconds. Electrons remained free for hundreds of thousands of years until the universe had cooled enough for atoms to form. The large-scale structures we see today, galaxies, stars, planets, were seeded by tiny fluctuations in the early plasma that grew under gravity's pull. The cosmos we inhabit was thus shaped by the physics of its earliest instance, when temperatures and energies were unimaginably high. Crucial to this story is the idea of symmetry breaking. In physics, symmetry means invariance, but symmetries can shatter as conditions change. Imagine water cooling into ice. The liquid state is symmetric, molecules moving freely without preferred directions. But as the temperature drops, the water freezes into a crystalline lattice, breaking the symmetry. The laws governing the particles remain the same, but their collective state changes. In the early universe, similar transitions occurred, not with water molecules, but with the fundamental forces themselves. Physicists believe that at very high energies, the electromagnetic and weak nuclear forces were unified into a single electro-weak interaction. As the universe cooled below a certain threshold, this symmetry broke, and the electromagnetic and weak forces separated, each taking on distinct properties. This process depended on the Higgs field, whose value set the masses of particles and defined the behavior of the forces. In other words, the constants of nature were determined not in eternity, but in an event of cosmic history. Even earlier, it is possible that the strong force too was unified with the electro-weak force in what physicists call a grand unified theory. If such a unification existed, then, as the universe cooled, it shattered into the distinct forces we know today. Gravity, the most enigmatic force, may also have joined this unity at energies near the Planck scale, only to separate as the universe cooled. The laws of physics as we know them may thus be relics of symmetry breaking, frozen accidents of cosmic history rather than eternal necessities. The inflationary epoch adds another layer to this story. Inflation is the idea that in the first tiny fraction of a second, the universe underwent a burst of exponential expansion. Space itself expanded faster than the speed of light, smoothing out irregularities and explaining why the cosmos is so uniform on large scales. Inflation also magnified quantum fluctuations, seeding the distribution of galaxies we see today. But inflation does more than solve cosmological puzzles. It suggests that different regions of space could end inflation in different ways, leading to different vacuum states and possibly different laws. Our universe could thus be one bubble among many, each with its own set of constants. This possibility makes the early universe a laboratory not just for cosmology, but for the question of whether laws are unique. If symmetry breaking and inflation determined the constants, then other outcomes might have been possible under slightly different conditions. The laws we observe may not be the only way reality can be structured. The evidence for this story is rich. The cosmic microwave background, the faint afterglow of the Big Bang, shows tiny fluctuations in temperature at the level of 1 part in 100,000. These ripples are the fingerprints of processes in the early universe, consistent with the predictions of inflation. The abundance of light elements, hydrogen, helium, and trace amounts of lithium matches the predictions of nucleosynthesis that occurred in the first few minutes. These lines of evidence anchor the story of the early cosmos in data, not speculation, and yet, much remains uncertain. We do not know whether inflation happened exactly as described, nor whether grand unification or other exotic physics occurred in the first instance. What we do know is that the laws and constants we now treat as fixed were shaped in that crucible. They are not eternal truths given from outside, but outcomes of processes in the unfolding universe. This realization reframes the puzzle. If the laws were born in time, then they might have been otherwise. If they might have been otherwise, then perhaps elsewhere they are otherwise. The emergence of laws in the early universe is not only a cosmological story, but a philosophical one. forcing us to rethink what it means for physics to be fundamental. The unfolding of the early cosmos can be imagined as a sequence of thresholds, each one transforming the character of physical law. In the first moments after the Big Bang, energies were so high that all the forces may have been united. As the universe expanded and cooled, one threshold after another was crossed, each breaking symmetries and locking in new rules. These transitions were not gentle but dramatic, like water freezing or iron becoming magnetized. They were cosmic phase changes, and they determined the nature of reality. One of the most important of these transitions was the breaking of electroweak symmetry. Before this event, there was no distinction between electromagnetism and the weak nuclear force. Afterward, the Higgs field settled into a particular value, giving masses to particles and separating the forces into the distinct forms we observe today. Had the Higgs field chosen a different value, the masses of particles might have been wildly different. Chemistry as we know it might not exist, and stars might never have formed. In this sense, the laws of our universe are not eternal, but crystallized outcomes of an event in its early history. The strong nuclear force also emerged through a phase transition. Quarks, once roaming freely in a hot plasma, became confined into protons and neutrons as the universe cooled. This confinement was irreversible, a permanent rearrangement of matter into bound states. The properties of the strong force, such as the fact that it grows stronger with distance rather than weaker, ensured that quarks would never again exist in isolation. This too was a turning point in the structure of the cosmos. Each transition was accompanied by the release of energy, shaping the evolution of the universe. These transitions might also have created relics such as cosmic strings or other topological defects, though no definitive evidence has been found. The possibility remains that traces of these primordial events could one day be discovered in the cosmic microwave background or in gravitational wave signals from the earliest times. Such discoveries would not only illuminate the birth of the universe but also reveal how the laws themselves were forged. Inflation adds an even more striking perspective. If inflation occurred, it means that our observable universe is just a tiny patch of a vastly larger whole. Inflation could create countless regions, each cooling and breaking symmetries in its own way. In some regions, the Higgs field might settle into different values, giving different particle masses. In others, the strengths of the forces might diverge from those we know. Each region would be a universe unto itself, with its own laws. In this picture, what we call the laws of physics are simply the local rules of our cosmic neighborhood. The observational evidence for inflation comes not only from the uniformity of the cosmos, but also from the spectrum of fluctuations in the cosmic microwave background. The pattern of ripples observed by satellites such as COBE, WMAP, and Planck matches the predictions of quantum fluctuations stretched by inflation. These results are compelling, though not definitive. Inflation explains much, but its underlying mechanism remains mysterious. It requires a field, often called the inflaton, whose properties are unknown. Whether such a field exists, and whether it truly drove inflation, is still under investigation. What is clear is that the early universe was a place where the familiar categories of physics were being written into existence. The constants we measure today, the masses of particles, the strengths of forces, the ratios that define chemistry and cosmology were fixed during these ancient transitions. If conditions had been slightly different, the outcomes could have been radically altered. Our laws are therefore not outside of time, but products of history. This view challenges the traditional notion of laws as eternal truths. It suggests instead that laws may be emergent, arising from deeper structures or processes that themselves are subject to change. Just as the crystalline structure of ice emerges from water at freezing, the framework of our universe may have emerged from a more symmetric and fluid reality at high energy. The constants are then like the angles of a crystal lattice, precise, measurable, and consistent, yet not fundamental in themselves. To contemplate this is to recognize the fragility of our assumptions. We call them constants, yet they may be the frozen accidents of a cosmic story. We call them laws, yet they may be local conditions in a larger reality. The early universe shows us that the very things we take as fixed may be contingent, and that the path to deeper understanding lies in unraveling how these laws came to be. The realization that the laws of physics emerged from the early universe has profound implications. It suggests that what we now treat as immutable features of reality are in fact historical outcomes. They were set during the first instance of cosmic time, shaped by processes we are only beginning to glimpse. This means the universe could have unfolded differently. If symmetry breaking had taken another path, if inflation had ended in another state, the constants and forces we take for granted might not exist in their present form. This line of thought helps explain why physicists consider the early universe not only a subject of cosmology, but also a laboratory of fundamental physics. It is the one place where energies were high enough to reveal the unification of forces, the dynamics of symmetry breaking, and perhaps even the fingerprints of a theory that combines quantum mechanics with gravity. By studying the relics of those early times, from the cosmic microwave background to the distribution of galaxies, we are in effect reading the script by which the laws of physics themselves were written. The cosmic microwave background offers a particularly powerful window. Its faint variations in temperature carry information about the density and composition of the universe when it was only a few 100,000 years old. The patterns align with the predictions of a universe governed by the laws we know, but they also leave space for surprises. Tiny anomalies, still debated, may hint at processes not fully understood. Future measurements, especially those targeting the polarization of the microwave background, may reveal signatures of gravitational waves from inflation. Such a discovery would not only confirm inflation, but also give us direct evidence of physics at energies otherwise unreachable. Gravitational waves themselves provide another way to probe the early universe. The mergers of black holes and neutron stars detected in recent years are just the beginning. In principle, gravitational waves could carry information from the very first moments after the Big Bang, ripples frozen into space-time itself. Detecting such primordial signals would open a new era of cosmology, one in which we study not just the aftermath of the early universe, but the actual birth of the laws. This picture, though still tentative, reframes the question of universality. If the laws of physics were born in time, then universality becomes a feature of our patch of the cosmos, not a guarantee across all reality. The laws may be universal within our horizon, but elsewhere, in regions born of different conditions, they might differ. This does not diminish their power but contextualizes it, placing our universe as one outcome among many possible ones. It also shifts how we think about necessity. For centuries, physicists believed the laws were necessary, that they could not have been otherwise. The early universe suggests instead that they are contingent. They depend on conditions, on history, on processes that unfolded in time. This contingency does not make them less real. It makes them part of the story of the universe, products of its evolution, rather than edicts imposed from outside. From this perspective, the question of whether the laws could differ is not abstract. It is grounded in the very origins of our cosmos. The forces and constants we know are the frozen results of cosmic events. If those events had gone differently, the laws would be different. Our universe, then, is not the only imaginable one. It is one possibility realized among many. This recognition prepares us for the next step. If the early universe shows that laws can emerge and differ, then the idea of multiple universes becomes less speculative. If inflation can produce many regions with different vacuum states, if symmetry breaking can yield different outcomes, then the multiverse is not a wild fantasy, but a natural extension of cosmology. The question becomes not whether other universes are possible, but what kinds of physics they might allow, and whether we can ever hope to detect their traces. Thus, as we leave the early universe, we carry with us a new vision of physical law, not as timeless decree, but as emergent outcome. To follow this vision further, we must step into the realm of multiverse frameworks, where theory suggests a vast landscape of universes, each with its own constants, its own symmetries, its own laws. The thought that our universe might not be alone has long lingered at the edge of human imagination. Myths and philosophies across cultures have envisioned countless worlds beyond our own, But in modern physics, the idea of a multiverse arises not from speculation, but from equations. The deeper we probe the fabric of reality, the more we find hints that what we call the universe may be just one pocket of a far larger whole. One of the most influential attempts to classify these possibilities comes from physicist Max Tegmark, who proposed 4 levels of multiverse. The first level is perhaps the least controversial. It arises directly from the standard cosmological model. If space is infinite, then regions far beyond our observable horizon must exist. These regions are governed by the same laws of physics, but their initial conditions may differ. Some may have more galaxies, others fewer. Some may be dense with stars, others sparse. In such an infinite cosmos, every possible arrangement of matter consistent with our laws will occur somewhere. This is not a different physics, only a different patch of the same physics extended without bound. The second level of multiverse introduces more radical variation. It arises from inflation, the exponential expansion of space, thought to have occurred in the early universe. Inflation may not end everywhere at once. Instead, it may continue indefinitely in some regions, while in others it stops, creating bubble universes. Each bubble can cool into its own cosmos, potentially with different constants of nature, depending on how symmetries break and fields settle. Our universe would then be one bubble in an endless froth, each bubble a separate universe with its own rules. This vision, though unproven, emerges naturally from inflationary theory, making it one of the most studied multiverse frameworks. The third level comes from the interpretation of quantum mechanics. In the many worlds view, every quantum event, with multiple possible outcomes, actually realizes all of them, each in its own branch of reality. When a particle has a probability to be here or there, it is not that it chooses one. Rather, the universe splits, one branch with the particle here, another with it there. These branches evolve independently, never interacting again, yet all are real. This view eliminates randomness by saying that all outcomes occur, though we perceive only one. If true, it means the cosmos is constantly splitting into a vast branching tree of universes, each as real as our own. The fourth level is the most speculative and perhaps the most dizzying. Tegmark suggested that all consistent mathematical structures exist as physical realities. In this view, mathematics is not just a language we use to describe the universe, but the substance of reality itself. Every coherent mathematical structure defines its own universe, with its own laws. Our universe is then simply one among an infinite library of mathematical realities. Though controversial, this idea pushes the boundaries of what it means for a universe to exist. Beyond Tegmark's taxonomy, physics offers further multiverse frameworks. String theory, one of the leading candidates for unifying quantum mechanics and gravity, predicts an enormous number of possible vacuum states, each corresponding to a different way of compactifying extra dimensions. The number of possibilities has been estimated as 10 to the power of 500 or more, a staggering landscape of potential universes. Our universe would then be one particular point in this landscape, with its specific constants and laws emerging from the shape of hidden dimensions. This landscape has been criticized as untestable, yet it arises directly from attempts to build a consistent theory of everything. If the theory is correct, then the existence of many possible universes is not optional, but inevitable. The challenge is to explain why we inhabit this one rather than another. Some physicists invoke anthropic reasoning. Among the vast possibilities, only a small fraction allow for complex structures, stars, planets, and life. We should not be surprised to find ourselves in such a rare universe, because it is the only kind in which observers could exist. Inflation and string theory together create one of the most developed scientific pictures of a multiverse. Eternal inflation produces endless bubble universes, while the string landscape provides the menu of possible laws each bubble might realize. The combination is speculative but mathematically consistent, rooted in mainstream physics rather than pure imagination. It offers a framework in which fine-tuning is no longer a mystery but a selection effect. In a vast ensemble of universes, some must fall into the narrow ranges that allow complexity. Yet the idea remains controversial. Critics argue that a theory that predicts everything predicts nothing. If all possible laws are realized somewhere, how do we test the framework? How do we make falsifiable predictions? Supporters reply that the multiverse may still leave signatures. Bubble collisions might leave imprints in the cosmic microwave background. Certain statistical distributions of constants may be more probable than others. While evidence is elusive, research continues, for the potential reward is nothing less than a new understanding of what it means to call something a law of physics. The possibility of a multiverse forces us to rethink the nature of explanation itself. In the past, science sought single laws that applied universally. Newton's laws described motion, Maxwell's equations described electromagnetism, and Einstein's relativity described gravity. The idea that there might be not one set of laws but many, each realized in its own universe, overturns that tradition. It suggests that what we call the laws of nature are local conditions, shaped by cosmic history and perhaps by chance. Eternal inflation provides a particularly vivid picture of how such a structure might arise. In this scenario, space is filled with a field whose energy drives rapid expansion. In some regions, the field decays, releasing energy that creates matter and radiation, giving birth to a universe like ours. But in other regions, inflation continues. The process never ends globally, creating an infinite patchwork of universes, each with its own initial conditions. Within each bubble, physics may differ depending on how fields settle into their vacuum states. To us, our universe feels all-encompassing, yet in this view, it is just one bubble in an endless sea. String theory deepens this vision. It suggests that the fundamental ingredients of reality are not point particles but vibrating strings, existing in more dimensions than the familiar 3 of space and 1 of time. These extra dimensions are compactified, curled up in tiny shapes beyond our perception. The way these dimensions are shaped determines the values of constants, the types of particles, and the strengths of forces. There are unimaginably many possible shapes, leading to the so-called string landscape. If eternal inflation is real, each bubble universe could sample a different region of this landscape, producing an immense diversity of laws. The implications are staggering. Our universe might be one of 10 to the power of 500 possible universes, each as real as ours, each with its own physics. This vast ensemble is not fantasy, but an outcome of serious attempts to unify the forces of nature. Yet it raises profound questions. If every possible law exists somewhere, why should we care about the particular values we see? What does it mean to explain why the fine structure constant is 1 over 137, if every other value exists in some universe too? Anthropic reasoning enters here as a controversial but unavoidable tool. It argues that we observe the values we do because only those values allow life and observers to exist. If the cosmological constant were much larger, galaxies would never form. If the strong force were slightly different, chemistry would collapse. Among the immense landscape of possibilities, only a sliver permits complexity. We live in that sliver because otherwise we could not exist. This reasoning is not satisfying to all, but it provides a framework for understanding fine-tuning without invoking design or necessity. Evidence for such a multiverse is elusive, but physicists search for indirect hints. One possibility is that if bubble universes collide, they might leave scars in the cosmic microwave background, subtle patterns that could be detected with precise observations. Some teams have claimed to see anomalies, though none have yet been confirmed. Another approach is statistical. If constants such as the cosmological constant fall into ranges predicted by anthropic reasoning within a multiverse framework, that consistency may itself be a kind of evidence. In this way, the multiverse is not beyond science but an extension of it, though the methods of testing are less direct than in traditional experiments. The idea also raises philosophical debates about what counts as science. Some argue that if other universes cannot be observed even in principle, the concept belongs to metaphysics, not physics. Others counter that if a theory like inflation predicts a multiverse, And if inflation is well supported by evidence, then we must take its implications seriously, even if they stretch beyond direct observation. After all, black holes were once considered unobservable, yet today they are confirmed through gravitational waves and imaging of event horizons. Science evolves, and what seems unreachable now may one day yield to ingenuity. The multiverse frameworks, whether from inflation, string theory, or quantum many worlds, may or may not describe reality, but they serve an important role. They remind us that the laws of physics we take as universal may be local, that what we see as necessary may be contingent, and that explanation itself may require a broader canvas. The notion of a multiverse is not simply a scientific proposal, but a challenge to our deepest intuitions. For much of history, the universe was seen as unique. Even when astronomy revealed countless stars and galaxies, they were all thought to share the same laws, bound together within a single cosmic stage. The multiverse idea dissolves that unity. It suggests that reality is not a single play, but a vast theater with countless stages, each with its own script. Quantum mechanics adds to this vision through the many worlds interpretation. In this framework, every quantum event branches reality. When an electron can pass through one slit or another, both outcomes occur, each in its own universe. When a radioactive atom has a chance to decay, both decay and non-decay happen, each in a separate branch. We experience only one branch, but the theory treats all as equally real. If this interpretation is correct, then the multiverse is not distant, but immediate, unfolding with every quantum choice. Though many worlds differs from inflationary or string theory multiverses, they all share a theme. The laws and outcomes we observe are not unique. Reality is broader than what we see, and our universe is one instance among many. Whether these instances differ in constants, in histories, or in both, the implication is the same. What we call universal laws may be only local rules. Critics warn of the danger of unfalsifiability, a theory that allows everything risks, explaining nothing. If every possible outcome happens somewhere, what predictions can we test? Supporters reply that even within a multiverse, probabilities matter. Some laws or constants may occur more frequently than others, and our universe may be typical or atypical within the distribution. By comparing predictions with observations, we may find consistency or tension. In this way, the multiverse can still guide scientific inquiry, even if direct observation remains beyond reach. The philosophical weight of the multiverse is immense. It shifts explanation from necessity to contingency. Instead of asking why the universe has these laws, we may ask why we observe them, and the answer becomes selection rather than uniqueness. This is unsettling, for it replaces definitive answers with probabilistic ones. Yet science has faced such shifts before. The Copernican revolution displaced Earth from the center of the cosmos. Darwinian evolution displaced humanity from a privileged creation. The multiverse may be the next step, displacing our universe from its imagined uniqueness. Despite its controversies, the multiverse frameworks are grounded in serious physics. They emerge from inflation, from string theory, from quantum mechanics, not from idle imagination. They may or may not describe reality, but they represent the frontier of our effort to understand why the laws are what they are. They also provide context for the puzzle of viability. If other universes exist, what kinds of physics might they allow? And what kinds of universes would collapse under their own contradictions? This question leads naturally to the next stage of inquiry. Having explored the frameworks of multiverse theory, we turn to the distinction between viable and non-viable universes. By asking what kinds of variations in constants or laws still permit complexity, we can map the boundaries of possibility. This exploration does not merely speculate about other worlds. It illuminates the delicate balance of our own, showing why our universe is as it is, and why small changes could make it very different. If the multiverse is real, then it may contain universes with laws and constants very different from our own. The natural question follows: which of these universes could sustain complexity, and which would collapse into barren simplicity. To explore this, physicists conduct thought experiments grounded in rigorous reasoning. They alter the values of constants in their equations, asking what kind of cosmos would result. The answers reveal just how delicately balanced our universe is, and how easily the conditions for life could vanish. Consider first the force of gravity. In our universe, gravity is by far the weakest of the known forces. A small magnet on a refrigerator can lift a paperclip against the pull of the entire Earth. Yet if gravity were only a few times stronger, stars would collapse more quickly under their own weight. Their nuclear furnaces would burn through fuel in millions rather than billions of years, leaving little time for planets to form or for life to evolve. If gravity were weaker, matter might never clump into stars at all, leaving a universe of diffuse gas. Either way, the balance between strength and weakness determines whether stable stars, the engines of complexity, can exist. The strong nuclear force provides another crucial example. As the glue that binds protons and neutrons inside atomic nuclei, its strength controls the formation of elements. If the strong force were slightly weaker, nuclei heavier than hydrogen would not hold together, and the periodic table would collapse into triviality. Without carbon, oxygen, or iron, there would be no chemistry, no planets, no life. If the strong force were slightly stronger, nuclear binding would be so tight that hydrogen would be rare, stars would burn differently, and water, the solvent of life as we know it, might never form. The weak nuclear force, though subtle, is equally important. It governs the reactions that allow stars like our Sun to shine steadily. If the weak force were much stronger, stars would burn through their fuel in a flash, flooding space with radiation, but leaving no time for stable planetary systems. If it were much weaker, nuclear reactions would stall, and stars would fail to ignite. Either extreme would erase the possibility of a habitable cosmos. The ratio of particle masses adds further constraints. The proton is about 1,836 times heavier than the electron. This disparity allows electrons to orbit nuclei at just the right distance to create stable atoms. If electrons were much heavier, atoms would shrink, and chemistry would unfold differently, perhaps too violently to permit stability. If electrons were much lighter, atoms would grow too diffuse, weakening chemical bonds and undermining the complexity of molecules. Once again, the balance seems finely poised. Even the number of dimensions plays a role. Our universe has 3 dimensions of space and 1 of time. If space had only 2 dimensions, gravity would not produce stable orbits, and planetary systems could not exist. If it had 4 or more spatial dimensions, the inverse square law of gravity would change, making orbits unstable. Planets would spiral into their stars or drift away, destroying the possibility of long-lived systems. The dimensionality of space, which might seem an abstract mathematical feature, turns out to be critical for the existence of complexity. These examples do not prove that our universe is uniquely fine-tuned for life, but they show that small deviations in constants often lead to barren outcomes. A stronger gravity, a weaker nuclear force, a different ratio of masses, or another number of dimensions, all could make the cosmos sterile. The range of viable possibilities appears narrow compared to the vastness of what could be imagined. The concept of viability is not restricted to life as we know it. Even if we set aside biology, complexity requires stable structures. Stars must live long enough to forge heavy elements. Atoms must bond into molecules. Planets must orbit stably around stars. These conditions are fragile. In many hypothetical universes, the ingredients of complexity evaporate before they can begin. In this sense, our cosmos is remarkable not because it supports life specifically, but because it supports structure at all. Physicist Steven Weinberg used this line of thought in analyzing the cosmological constant. If the constant were much larger, galaxies would never have formed, as cosmic acceleration would tear matter apart too quickly. If it were much smaller and negative, the universe might have collapsed back into itself. The observed value, though puzzling, lies in the narrow range that permits galaxies, stars, and planets. Weinberg argued that this is exactly what we should expect in a multiverse. Only universes with constants compatible with structure, can host observers. The study of viable and non-viable universes is therefore more than speculation. It is a way to map the boundaries of possibility, to understand which regions of the landscape of laws allow complexity and which lead to emptiness. By charting these boundaries, physicists gain insight into why our universe looks the way it does, and why the constants we measure fall within their life-permitting ranges. Exploring possible universes is not a matter of idle fantasy. It is a scientific exercise in counterfactual reasoning, grounded in equations and simulations. By altering parameters in theoretical models, physicists can see how stars would evolve, how atoms would bond, and how cosmic structures would form under different laws. These explorations reveal both the fragility and the robustness of physical reality. For example, researchers have studied what would happen if the ratio of electromagnetic to gravitational force were changed. In our universe, this ratio is about 10 to the power of 36. This immense disparity allows stars to balance gravity's inward pull with the outward pressure of nuclear fusion. If electromagnetism were weaker or gravity stronger, this balance would collapse. Stars would be unstable, burning too fast, or never forming at all. If electromagnetism were stronger, chemistry itself might fail, with electrons clinging too tightly to nuclei to allow complex molecules. Another axis of variation involves the relative strengths of the nuclear forces. If the strong force were altered, the production of elements in stars would change drastically. A slightly weaker strong force would prevent the fusion of helium into carbon, erasing the possibility of carbon-based life. A slightly stronger strong force might make carbon too stable, trapping nuclear reactions and preventing the synthesis of oxygen. In both cases, the chain of element production that gives us the periodic table would break, and with it the possibility of chemistry as we know it. The role of dimensionality illustrates another profound limit. In two spatial dimensions, the gravitational potential behaves differently, and stable planetary orbits are impossible. In 4 or more spatial dimensions, the inverse square law generalizes into steeper or shallower power laws, destabilizing atomic and planetary systems alike. Our universe's 3 dimensions of space are not arbitrary. They appear to be the only case where complex structures can persist. Even time plays a role. A universe with 2 dimensions of time, rather than 1, would lead to chaotic trajectories, undermining causality itself. The flow of time in one direction appears essential for coherent evolution, for cause and effect, and for the unfolding of complexity. While it is difficult to imagine alternative temporal structures, mathematics shows that they would lack stability, reinforcing the specialness of our single time dimension. Physicists have also modeled variations in the ratio of fundamental particle masses. If the neutron were only slightly lighter than the proton, hydrogen would be unstable, decaying into neutrons and electrons. Without hydrogen, stars would lack the primary fuel that ignites fusion. If the neutron were much heavier, nuclei beyond hydrogen would be unstable, collapsing back into protons. Either way, the periodic table would vanish. Our particular mass difference, small in absolute terms but crucial in effect, allows for the existence of both hydrogen and heavy elements, the twin foundations of stars and chemistry. These counterfactual experiments show that the universe occupies a narrow corridor of viability. Step too far in any direction, and the structures that make complexity possible dissolve. This corridor is not infinitely thin. There may be room for variation, but it is narrow compared to the vast space of possibilities. The rarity of viable conditions raises the question of how they came to be realized. Some physicists take this as evidence for deeper principles. Perhaps the constants are not free to vary, but are determined by mathematical necessity. If so, our universe is not lucky, but inevitable. Others embrace the multiverse picture, in which countless universes exist with different values, and we inhabit one of the rare viable ones. Still others hold that the puzzle is unsolved, awaiting a breakthrough in understanding that will reveal why our constants fall where they do. The study of viable and non-viable universes thus illuminates both our ignorance and our insight. We can show that small changes would erase complexity, but we cannot yet explain why the constants are poised where they are. What we do know is that our universe is remarkable not because it exists, but because it exists in a form that allows stars to shine, atoms to bond, and minds to ask these questions. The mapping of possible universes highlights a profound truth. Physics is not only about describing what is, but also about imagining what could be. By testing how far the laws can be bent before complexity disappears, scientists gain perspective on why our universe has the shape it does. This perspective sharpens our sense of contingency. The constants are not simply numbers on a chalkboard. They are the difference between a cosmos alive with stars and a void where nothing endures. Some scenarios produce universes that exist but are sterile. A cosmos with only hydrogen might expand, cool, and persist for billions of years, but it would lack chemistry beyond the simplest atom. No carbon chains, no oxygen molecules, no rocky planets. Another scenario yields a universe of dense radiation, too hot for stable structures, collapsing into black holes before galaxies can form. These universes are not impossible, but they are non-viable for complexity. They remind us that longevity alone is not enough. It is the emergence of stable structures that defines viability. Other scenarios push further, imagining universes with different numbers of dimensions or altered forms of quantum mechanics. In many cases, mathematics shows that such universes collapse almost immediately. Without stable orbits, without predictable causality, without quantum stability, they cannot sustain even the simplest forms of order. In this sense, viability appears to be a rare property, one that depends on a delicate interplay of factors. The anthropic principle again enters this conversation, not as an explanation, but as a reminder. We find ourselves in a universe that allows complexity because only such a universe could host beings capable of noticing. This does not solve the puzzle, but it frames it. Out of the vast space of possibilities, only a narrow corridor permits observers. The fact that we are here suggests that our universe lies in that corridor, but it does not explain why. Physicists such as Steven Weinberg have used this reasoning to make predictions. Weinberg argued that if the cosmological constant were much larger, galaxies would never form, so observers could not exist. From this, he predicted that the constant would not be zero but small and positive, within a range that allows galaxies. When the accelerated expansion of the universe was discovered in the 1990s, it matched this expectation. This was not proof of the anthropic principle, but it showed how thinking about viability can guide scientific reasoning, even in the absence of deeper theory. The exploration of viable and non-viable universes also raises philosophical questions. What does it mean to say a universe is possible? Is it enough that it can be described by consistent mathematics, or must it be realized in some physical sense? If mathematics permits infinite variations, does that mean infinite universes exist, or is possibility narrower than imagination? These questions blur the line between physics and philosophy, yet they arise naturally from the study of fine-tuning. In the end, the exercise reveals both the fragility and the resilience of physical law. Fragility, because small changes can erase complexity. Resilience, because within the narrow corridor of viability, stars and galaxies arise naturally, chemistry flourishes, and life can emerge. Our universe balances between these extremes, poised on parameters that allow both stability and richness. This balance is not yet explained. Perhaps it reflects necessity, perhaps chance, perhaps deeper laws still hidden. But it frames the next question. If other universes exist, could we ever hope to detect them? Or is the idea of a multiverse forever beyond the reach of observation? To answer this, we must turn from thought experiments to the search for evidence, from the theoretical landscape to the data written in the sky. The idea of other universes, though compelling, demands more than imagination. Science advances not by speculation alone, but by evidence. If the laws of physics could differ elsewhere, then the challenge is clear. Can we ever detect traces of those other possibilities? Can we test the multiverse with observations as rigorous as those that confirmed relativity or quantum mechanics? The task is daunting, but researchers have begun to outline ways that evidence might be sought. The most direct place to look is the sky itself. The cosmic microwave background, the afterglow of the Big Bang, offers a map of the infant universe. Tiny variations in its temperature and polarization reveal the physics of the first moments after expansion. If our universe were one bubble in a larger multiverse, then collisions between bubbles might have left scars. These would appear as circular anomalies or unusual patterns in the microwave background, subtle signals imprinted billions of years ago. Over the past 2 decades, satellites such as WMAP and Planck have measured the microwave background with exquisite precision. The results reveal a cosmos astonishingly uniform, with fluctuations at the level of 1 part in 100,000. Yet, within this smoothness, anomalies have drawn attention. A cold spot larger than expected, slight asymmetries between hemispheres, and other irregularities have been reported. Some researchers suggest these could hint at bubble collisions. Others argue they are statistical flukes or artifacts of data analysis. So far, no anomaly has been confirmed as a signature of another universe. Gravitational waves provide another frontier. These ripples in space-time, first detected in 2015, open a new way of observing the cosmos. If inflation occurred, it should have produced a background of primordial gravitational waves, faint echoes from the earliest fraction of a second. Detecting such a background would not only confirm inflation, but could also hint at processes that generate multiple universes. Instruments like LIGO and Virgo are sensitive to gravitational waves from black hole mergers, while future missions like LISA may probe longer wavelengths that carry information from the dawn of time. Particle physics offers indirect approaches as well. If constants vary across a multiverse, then the distribution of their values may be constrained. For example, Steven Weinberg predicted that if the cosmological constant could vary, then observers would only find themselves in universes where it is small enough to allow galaxies to form. The discovery of cosmic acceleration in the 1990s, with a cosmological constant, small but non-zero, matched this expectation. Though not a proof of the multiverse, it illustrated how reasoning about viability can yield correct predictions. Still, the challenge of evidence remains immense. By definition, other universes may lie beyond our observable horizon, unreachable by light or signal. How, then, can we hope to test their existence? Some argue that indirect evidence is enough. If a theory such as inflation predicts a multiverse, and if inflation is strongly supported by observations, then we must take its implications seriously. Others counter that until specific, falsifiable predictions are made and tested, the multiverse remains a hypothesis on the edge of science. The debate reflects a tension at the heart of physics. On one hand, we demand empirical confirmation. On the other, we recognize that some ideas may stretch the limits of what can be directly observed. Black holes were once thought forever hidden, yet now we detect their mergers and even capture images of their shadows. Perhaps the multiverse, though distant, will one day yield evidence through subtle imprints on the sky, or through the statistical patterns of constants. The search for traces of other universes does not end with the microwave background or gravitational waves. Precision cosmology itself offers clues. By mapping the distribution of galaxies across billions of light-years, astronomers can test whether the universe is as uniform as theory predicts. Small deviations, unexpected alignments, or unusual voids might point to influences beyond our cosmic horizon. While no such evidence has yet been confirmed, the tools of large-scale surveys are becoming sharper, with projects like the Dark Energy Survey and the upcoming Euclid mission promising to refine our picture of cosmic structure. Another approach considers whether constants measured in our universe follow a distribution expected in a multiverse. If constants can vary, then their values across universes might form a spectrum. Within that spectrum, only a small fraction will allow observers. Our own constants should then appear typical within that life-permitting subset. The cosmological constant again provides an example. Its observed value is small, puzzlingly small compared to naive theoretical predictions, yet it lies just within the range that allows galaxies to form. Some interpret this as evidence that we live in a multiverse, where only universes with similar values are observed. This line of reasoning has critics who argue that it risks circularity. We observe the values we observe because we are here, but does that really explain them? Without independent confirmation of other universes, anthropic reasoning remains philosophical rather than empirical. Still, the fact that it led Weinberg to anticipate the order of magnitude of the cosmological constant lends it weight. Even if unsatisfying, it may be the best guide available until deeper theory or clearer evidence emerges. Laboratory experiments also contribute. Though they cannot create new universes, they can test whether our laws are absolute or contingent. Searches for variation in constants, precision measurements of particle interactions, and attempts to detect exotic fields all probe the boundaries of known physics. If anomalies were found, they might hint that our universe is part of a larger ensemble, its constants shaped by broader principles. So far, the results reinforce stability, but the search continues with ever-increasing precision. The challenge is not only technical, but conceptual. How do we recognize evidence for something beyond our universe? A collision between bubble universes might leave a mark in the sky, but distinguishing it from statistical noise is difficult. A prediction from anthropic reasoning might match observation, but is that proof or coincidence? The standards of science demand caution, yet the scale of the question invites boldness. We are confronted with the paradox of trying to observe the unobservable, of trying to test the possibility that our universe is not alone. In this tension lies the strength of scientific humility. The multiverse cannot be dismissed out of hand, for it arises naturally from theories already supported by evidence. Yet it cannot be embraced uncritically, for evidence remains elusive. The balance is delicate. Physicists walk a line between skepticism and openness, knowing that great discoveries often begin as ideas that seemed impossible to test. The quest to find traces of other universes has already reshaped the boundaries of scientific thought. Even without definitive evidence, the very act of asking the question forces physics to confront what counts as explanation and what counts as testable knowledge. It reminds us that science is not a static body of facts, but a process of pushing against the limits of the knowable. The cosmic microwave background remains one of the most promising avenues. If collisions between bubble universes occurred, they might have left telltale rings or alignments frozen into the ancient light. While no confirmed signal has yet been found, future missions with greater sensitivity may sharpen the search. Gravitational wave observatories may also one day detect signals from inflation, carrying echoes of processes that could give rise to a multiverse. Even a negative result would be meaningful, ruling out classes of models and guiding theory toward more constrained possibilities. On Earth, experiments with ever more precise instruments will continue to probe the stability of constants, the behavior of fundamental particles, and the nature of dark matter and dark energy. Each measurement either confirms the remarkable precision of our framework or exposes cracks where new physics may emerge. In both cases, the outcome deepens our understanding of whether our universe is unique or part of something larger. At the heart of this pursuit lies the question of falsifiability. Can the existence of other universes ever be ruled out or confirmed? Some argue that if no test can be imagined, the concept belongs outside science. Others argue that indirect evidence, such as statistical predictions or subtle cosmic signatures, may suffice. After all, black holes were once considered unobservable, yet they are now among the best confirmed phenomena in astrophysics. The same could one day be true of the multiverse. The search for evidence is not only about proving or disproving the existence of other universes, it is also about expanding the scope of scientific imagination. By testing the edges of our theories, we refine our understanding of what laws mean, of how constants are set, and of whether our universe is typical or exceptional. Even if no evidence for other universes is ever found, the pursuit itself enriches physics, sharpening its tools and clarifying its boundaries. As we close this chapter, the lesson is one of cautious openness. The multiverse remains a hypothesis, not a proven fact, yet it arises from serious physics, not idle speculation. Its potential evidence lies in the sky, in the lab, and in the logic of theoretical models. Whether or not we ever confirm its existence, The very act of searching forces us to rethink what it means for laws to be universal. From here, the journey turns philosophical once more. If the laws we observe are not unique, then what does that say about the nature of law itself? Are the laws of physics descriptive, merely patterns we observe, or prescriptive, rules that the universe must follow? To explore this, we step beyond evidence into the realm of reflection, rethinking the very concept of physical law. We have journeyed from the solidity of modern physics to the fragile possibilities of fine-tuning, to the speculation of multiverses and the tentative search for evidence. At each step, the same question rises. What does it mean to call something a law of physics? Are these laws eternal truths, built into the foundation of reality, or are they descriptive patterns, summaries of how our universe happens to behave? The history of science shows how this question has evolved. In the 17th century, Isaac Newton described the motion of planets and falling apples with equations so precise that they seemed like timeless decrees. For more than 2 centuries, Newton's laws were treated as absolute, written into the structure of the cosmos itself. Then Albert Einstein showed that they were approximations, valid at low speeds and weak gravity but not at extremes. Suddenly, what had seemed eternal was revealed as contingent, part of a larger framework. This lesson echoes today. Our current laws, though astonishingly accurate, may be approximations as well. The idea that laws are descriptive rather than prescriptive gains strength from this history. A prescriptive law would dictate how reality must behave, like a rule enforced from outside. A descriptive law simply records the regularities we observe, distilled into equations. The motion of planets follows Newton's law of gravitation, not because the universe reads an instruction book, but because the patterns of mass and motion can be summarized in that way. In this sense, laws are human constructs, our best attempts to capture the order of nature. Yet the descriptive view leaves questions unsettled. Why are the patterns so mathematical, so precise, so universal within our horizon? Why do they hold across billions of light years and billions of years of cosmic history? If they are mere descriptions, why do they not break down more often? Why do they hold with such extraordinary fidelity? This puzzle leads some to favor the prescriptive view that the laws are real features of the universe, independent of human observation. The debate has echoes in philosophy. Are laws necessary truths, like mathematical theorems, or are they contingent facts, like the weather on a given day? The success of science lies partly in not answering this definitively, but in working with the laws as tools, refining them when anomalies appear. Still, the multiverse idea sharpens the stakes. If other universes exist with different laws, then laws cannot be necessary in the strictest sense. They would be contingent on conditions, products of history, rather than eternal truths. This shift parallels earlier revolutions. The Copernican revolution dethroned Earth from the center of the cosmos. Darwin's theory of evolution dethroned humanity from special creation. The multiverse and fine-tuning may now dethrone our laws from necessity. Just as Earth is one planet among many, and life on Earth is one outcome among many, so the laws we observe may be one set among many. What we call universality may be local circumstance. This perspective is unsettling but also liberating. It means that explanation may not end with a single final law, but may require a hierarchy of conditions. It invites us to see laws as emergent, arising from deeper levels of structure, shaped by symmetry breaking, history, and chance. They are no less real for being contingent, but their reality is dynamic rather than absolute. From this viewpoint, the constants and symmetries we take as given are like the grammar of a language. They allow sentences to be spoken, but they are not the only grammar possible. Other grammars exist, and other universes may speak them. Our laws are one language of reality, but not the only one. The distinction between descriptive and prescriptive laws is not just a matter of philosophy. It shapes how we interpret the fine-tuning of constants and the possibility of other universes. If the laws are prescriptive, fixed by some ultimate necessity, then fine-tuning is an illusion, and the values of constants could not have been otherwise. If the laws are descriptive, then fine-tuning becomes a real puzzle, suggesting that our universe is one contingent outcome among many possibilities. One way to think about laws as contingent is to view them as emergent. In this perspective, the laws we observe today arise from deeper processes, much as the patterns of weather emerge from the dynamics of atmosphere and ocean. The weather is not dictated by eternal truths, but arises from conditions that change with time. Likewise, the laws of physics may emerge from the conditions of the early universe, shaped by symmetry breaking and cosmic history. They are reliable within our horizon because those conditions are fixed, but they need not be universal beyond it. Examples of emergence already exist within physics. The laws of thermodynamics, for instance, are not fundamental in the same way as quantum mechanics. They describe the behavior of large collections of particles, summarizing patterns that arise from underlying microphysics. Entropy increases not because it must as a commandment, but because of the statistical behavior of vast numbers of particles. In this way, thermodynamic laws are real and powerful, yet they are emergent. Could the same be true of all laws, even the ones we think of as most fundamental? Some philosophers and physicists argue that this is likely. If constants are set by fields that froze during the early universe, then the values we observe are emergent outcomes. If the dimensionality of space results from stability conditions, then it too is emergent. In this view, the deeper we probe, the more we will find that laws are not ultimate decrees, but frozen accidents, crystallized from deeper structures. Others resist this idea, arguing that without fixed prescriptive laws, explanation becomes unmoored. If everything is contingent, then why do the deeper structures exist at all? Why does mathematics apply with such power? Why is there order rather than chaos? These questions point toward the possibility of meta-laws, principles that govern even the emergence of laws, a subject we will soon explore. For now, it is enough to recognize that rethinking the nature of laws is necessary if we take the multiverse seriously. The very idea of multiple universes with different laws forces us to see our own laws as contingent. They are patterns that describe our reality but need not describe all of reality. This realization reshapes how we think about science itself. It does not weaken science. On the contrary, it strengthens it by clarifying its role. Science does not hand us ultimate truths carved into the structure of existence. It gives us the best descriptions available, tested by experiment, refined by observation, and open to revision. Laws are the distilled patterns of reality as we experience it. Their power lies not in their absoluteness, but in their reliability. To accept this view is to embrace humility. The laws we know are astonishingly successful, but they may not be final. They may not even be unique. They are our window into reality, but the landscape of reality may be broader than any single set of laws can capture. The recognition that laws may be contingent rather than necessary alters our perspective on the search for ultimate explanations. If laws can differ across universes, then we cannot expect a single timeless principle to account for every detail of our cosmos. Instead, we must see the laws as local features, arising from deeper structures that allow variation. This does not diminish their validity within our universe, but places them in context, as one instance in a larger mosaic of possibilities. This shift also changes how we think about universality. For centuries, science has pursued the universal, the principles that hold everywhere and always. Yet if the multiverse is real, universality itself becomes local. The speed of light, Planck's constant, the fine structure, constant, these may be universal within our horizon, but they may not be universal in the deepest sense. They may be parameters that vary from one universe to another, stable here but different elsewhere. Our confidence in their universality reflects the scale we can observe, not necessarily the scale of all reality. Still, the concept of law remains indispensable. Even if laws are contingent, they are not arbitrary. They capture real regularities, patterns that can be tested, trusted, and applied. The power of physics lies in its ability to predict, and that power remains intact, whether the laws are necessary truths or emergent descriptions. What changes is the scope of explanation. Instead of seeking a final law that explains everything, we may seek a hierarchy of explanations, from the local patterns we observe to the deeper structures that permit many possible patterns. This hierarchy does not end the quest for understanding, but redirects it. It encourages us to search for the conditions that give rise to laws, to uncover the mechanisms of emergence, and to map the space of possibilities. It also invites humility, for it shows that our knowledge, however powerful, is not absolute. Our laws are astonishing achievements, but they may be provisional chapters in a larger story that stretches beyond our universe. The idea that laws are contingent also resonates with broader shifts in human thought. The Copernican revolution taught us that Earth is not the center of the cosmos. Darwinian evolution taught us that humanity is not a privileged creation. The recognition that our laws may not be unique continues this trajectory, removing yet another pedestal on which we once placed ourselves. It reveals a cosmos where even the rules are not guaranteed to be singular. This recognition does not diminish the beauty of science. On the contrary, it enriches it. The laws we know are extraordinary not because they are necessary, but because they work so well, describing our universe with precision across scales of time and space. They are valuable not because they are eternal, but because they reveal order in the midst of possibility. To rethink the nature of laws is not to weaken science, but to deepen it, to see it as a living endeavor rather than a fixed monument. From this vantage point, a new question arises. If the laws of physics are contingent, then is there a deeper principle that governs their emergence? Is there a meta-law, a framework beyond the laws themselves, that shapes which laws can exist and how they vary? This question leads us to the next step in our journey, where we search for meta-laws and deeper explanations that might unify the multiplicity of possibilities into a coherent vision of reality. If the laws of physics in our universe are contingent, then we must ask whether there exists a deeper framework that governs the emergence of laws themselves. Could there be meta-laws, principles that shape which universes are possible, which constants are permitted, and which structures can arise? Or does explanation dissolve into an infinite regress, each layer of law resting on a deeper one, with no ultimate foundation? The search for a meta-law begins with the quest for unification. For more than a century, physicists have sought a theory of everything, a framework that would unite general relativity, which governs the large-scale structure of the cosmos, with quantum mechanics, which rules the microscopic realm. The two are individually successful beyond measure, yet they remain mathematically incompatible. Gravity refuses to fit within the quantum framework, and quantum mechanics struggles to describe the smooth geometry of spacetime. If these two pillars can be joined, the result may reveal not only the laws of our universe, but the principles that shape all possible universes. One candidate for such unification is string theory. In this vision, the fundamental entities are not point particles, but vibrating strings, whose modes of vibration correspond to different particles. String theory naturally incorporates gravity, something that other attempts have failed to do. It also requires extra dimensions of space beyond the familiar three. The shapes of these hidden dimensions determine the properties of particles and the strengths of forces. This means that the laws we observe are not fundamental, but consequences of the geometry of unseen spaces. In this sense, string theory offers a candidate meta-law. The rules of geometry in higher dimensions determine the laws of physics in our universe. Another approach is loop quantum gravity, which attempts to quantize spacetime itself. Instead of treating spacetime as continuous, it describes it as woven from discrete loops, a fabric with a granular structure at the Planck scale. If correct, this would mean that the smooth geometry of general relativity is an emergent phenomenon, much like the smooth surface of water arises from countless molecules. The laws of spacetime would then be emergent from deeper quantum structures, another form of meta-law. Beyond these specific theories lies a more radical proposal, that mathematics itself is the ultimate reality. Max Tegmark has argued that every consistent mathematical structure exists physically. In this view, our universe is not chosen or selected, but simply one among an infinite set of mathematical possibilities. The meta-law is then nothing more than consistency. Any mathematical structure that does not collapse into contradiction exists as a universe. This idea is breathtaking in scope but controversial, for it blurs the line between mathematics and physics, between description and reality. The appeal of meta-laws lies in their promise of explanation. If the constants and symmetries of our universe are contingent, then a meta-law might tell us why these contingencies exist at all, why some possibilities are realized, and others are not. Yet the danger is that meta-laws may simply shift the question. If string theory explains our laws by invoking extra dimensions, we must still ask why those dimensions have their shapes. If loop quantum gravity explains space-time as emergent, we must still ask why its loops exist. If mathematics explains everything, we must still ask why mathematics itself exists. This is the challenge of infinite regress. Each explanation points to a deeper layer, but the chain may never end. Perhaps there is no final law, no ultimate foundation. Perhaps explanation is an endless descent, with each level emergent from another. Or perhaps there is a bottom, a principle so fundamental that no further question can be asked. The dream of physics has always been to find that bottom, to uncover the final law. But whether such a law exists remains uncertain. The pursuit of meta-laws is more than an intellectual exercise. It reflects a human longing for completeness, the desire to know not only how the universe works, but why it works that way. Physicists often speak of a final theory, a framework so fundamental that it leaves no questions unanswered. Yet, even this ambition carries uncertainty. Would such a theory truly end inquiry, or would it simply shift the questions into a new language? String theory offers a vivid example of this tension. On one hand, it unites gravity and quantum mechanics in a single framework, a feat unmatched by other theories. On the other, it produces a vast landscape of possible solutions, with different shapes of hidden dimensions giving rise to different laws. Instead of narrowing to one universe, string theory seems to allow an enormous number, perhaps 10 to the power of 500 or more. Some interpret this as failure, others as success. If the landscape is real, then it may be the meta-law itself. Reality allows all possibilities, and our universe is one among them. Explanation then shifts from necessity to selection, from why these laws to why we observe these laws. Loop quantum gravity, though less flamboyant in scope, also reframes our understanding. By quantizing space-time, it suggests that geometry is not fundamental, but emergent. The smooth fabric of relativity arises from a granular network of loops, like a tapestry woven from threads. If true, this means that even space-time itself is not a final law, but a phenomenon arising from deeper structures. The laws of physics we know are then emergent from a web of quantum geometry, and those in turn may be emergent from something deeper still. Other approaches explore holographic principles, where the information of a volume of space can be described by a theory defined on its boundary. This suggests that space-time and gravity themselves may not be fundamental, but holographic projections of more basic degrees of freedom. If so, then the laws we take as primary are shadows of deeper rules. The meta-law might be that reality is holographic, with many possible ways to project consistent universes. These proposals illustrate both the promise and the difficulty of meta-laws. They give us powerful tools to explain the laws we know, yet they do not silence all questions. If string theory explains constants through extra dimensions, why those dimensions? If loop quantum gravity explains space-time as emergent, why those loops? If holography explains geometry as projection, why that projection? Each answer invites a deeper question, and the regress continues. Philosophers of science caution that the dream of a final law may be an illusion. Perhaps reality is layered without end, with each level emergent from another, never arriving at a single foundation. In this view, the search for meta-laws is not a quest for closure, but an infinite journey. Each step brings greater understanding, yet the horizon recedes. this need not diminish science. On the contrary, it may enrich it, turning explanation into a process without end, a mirror of the infinite richness of reality itself. Still, the hope for a final principle remains. Many physicists believe that the simplicity and elegance of mathematics hint at deeper necessity. The unification of forces at high energies, the mathematical beauty of symmetries, the precision of quantum field theory, these suggest that there may indeed be a fundamental law waiting to be uncovered. Whether it will resolve the puzzle of contingency or reveal new layers of possibility is unknown. The search for meta-laws brings us to the boundary between science and philosophy, where the questions become as much about meaning as about mechanism. If there is a final law, it would be the deepest achievement of human thought, the culmination of centuries of inquiry. But if no such law exists, if explanation stretches into an endless regress, then the lesson is different, but no less profound. The richness of reality cannot be compressed into a single principle. It is layered, open, and inexhaustible. Some thinkers embrace the possibility that mathematics itself is the ultimate foundation. In this view, every consistent structure exists, and our universe is one among them. The only meta-law is consistency, the demand that contradictions cannot survive. This vision is austere yet expansive, replacing the dream of one final law with the vision of infinite mathematics. Others reject this, insisting that physical existence cannot be reduced to abstract logic, that something beyond mathematics grounds reality. The debate remains unresolved, and perhaps it always will. Another possibility is that the quest for meta-laws reveals the limits of human cognition. Our minds evolved to navigate survival on a small planet, not to grasp the foundations of all reality. The fact that we can probe as far as we do is remarkable, but perhaps our capacity for explanation is finite. Just as a dog cannot understand calculus, we may be unable to grasp the ultimate structure of existence. If so, the regress of explanation may end not because there is no final law, but because we lack the capacity to perceive it. Yet humility does not cancel hope. History shows that the limits of one era become the breakthroughs of the next. Once, atoms were thought indivisible, then discovered to be composed of protons, neutrons, and electrons, then those in turn of quarks and gluons. Each time the supposed foundation gave way to deeper structure. The regress has so far been fruitful, expanding knowledge rather than paralyzing it. Perhaps the same will be true of meta-laws. Each step deeper may open new insights, whether or not the end is ever reached. In this light, the question of meta-laws becomes less about closure and more about perspective. The goal is not necessarily to find the single principle that ends all questions, but to map the architecture of explanation, to understand how laws emerge, how constants are set, and how possibilities unfold. Even if the journey has no end, it is worth traveling. The pursuit itself reveals the depth of reality and the creativity of the human mind. As we close this chapter, the lesson is one of balance. We must seek meta-laws with rigor, testing, string theory, loop quantum gravity, holography, and other approaches. But we must also accept the possibility that no final answer exists. That explanation is an infinite horizon. In either case, the quest transforms our view of the universe. It shows that the laws we know are not the whole story, that behind them may lie deeper principles, and behind those, perhaps more still. The journey does not end here. Having explored meta-laws and deeper explanations, we turn finally to the question of perspective. What does it mean for science and for humanity to live in a universe where the laws themselves may be contingent? How do we embrace the humility that such a vision demands, while still celebrating the power of the knowledge we have gained? These reflections await in the epilogue, where we step back from equations to consider what the story of physical law tells us about our place in the cosmos. We have traced a long path, from the solidity of Newton's mechanics to the uncertainty of quantum theory, from the stability of constants to the fragility of fine-tuning, from the early universe to the possibility of a multiverse, and finally to the idea of meta-laws that may or may not end the chain of explanation. Along the way, a single theme has emerged. The universe is richer, stranger, and more contingent than our ancestors ever imagined. The laws of physics, once thought eternal, now appear as outcomes of history, products of symmetry breaking, cosmic cooling, and perhaps deeper mathematical structures. The constants we measure so precisely could have been different, and if they had been, stars might never have shone, atoms might never have bonded, and life might never have stirred. The realization that our universe occupies a narrow corridor of viability invites both wonder and humility. This humility is not weakness but strength. Science does not shrink when it admits uncertainty. It grows. The willingness to question, even the most fundamental assumptions, is the engine of discovery. It was humility that allowed Copernicus to move Earth from the center, humility that allowed Darwin to see humanity as part of evolution, humility that allowed Einstein to revise Newton. Each act of humility expanded our vision of reality. Now, the possibility of multiple universes and contingent laws may be the next expansion, reminding us that even the rules we rely on are not guaranteed to be unique. At the same time, we must celebrate what we have learned. Our universe is comprehensible to an astonishing degree. From the orbit of planets to the spectrum of atoms, from the ripples of space-time to the birth of galaxies, we can describe the cosmos with precision across billions of light years and billions of years of time. That such comprehension is possible at all is itself a wonder. Whether or not our laws are universal in the deepest sense, within our horizon, they are powerful, reliable, and beautiful. The future of physics may lie in deeper unification, in new experiments that test the stability of constants, in gravitational wave observatories that listen to the whispers of the early universe, and in mathematical frameworks that seek meta-laws. Or it may lie in the recognition that no final law exists, that explanation is an infinite horizon. Either way, the pursuit will continue, driven not by certainty, but by curiosity. The story of science is not the story of reaching an end, but of opening ever wider doors. To embrace cosmic humility is to accept that we may never have the final word, but that each word we write brings us closer to understanding. The laws of physics may differ elsewhere, or they may not. Our universe may be one among many, or it may be unique. We do not yet know. But in the act of asking, of searching, of testing, we fulfill the deepest impulse of human thought, to wonder at reality and to seek its order. The humility born of this journey is not resignation, but perspective. To recognize that our laws may be contingent is to place ourselves within a larger story. It is to see that the cosmos is not tailored for us, but that we are the outcome of its delicate balances. This recognition deepens rather than diminishes our sense of wonder. The stars shine not because they were meant to, but because the forces and constants allow them to. Life exists not because it was guaranteed, but because within a narrow range of possibilities, it became possible. This perspective also shapes how we think about knowledge itself. Science is not a quest for immutable truths, but for better descriptions, more accurate models, and deeper patterns. Each theory is provisional, awaiting refinement or replacement when new evidence arises. This openness is not a weakness, but the very strength of science. It allows progress without the illusion of finality. The recognition that laws may vary across universes only reinforces this strength, reminding us that the task of science is to describe what is observed, not to declare eternal decrees. In this light, the multiverse is less a challenge to science than a continuation of its spirit. It is an audacious hypothesis, born not of fantasy, but of equations. It stretches the boundaries of testability, yet it emerges from theories already grounded in evidence. Even if other universes remain forever beyond reach, the act of considering them sharpens our sense of what counts as explanation. It reminds us that universality is not assumed, but tested, and that the scope of our knowledge is always provisional. The possibility of meta-laws adds another layer to this humility. Whether the chain of explanation ends with a final principle, or stretches into infinity, we are reminded that our knowledge is part of a larger whole. We may never see the full picture, but each step toward it reveals more of reality's depth. To live with uncertainty is not failure, but a mark of maturity, the recognition that truth is vast and our grasp partial. What remains constant through all these possibilities is the human impulse to wonder, from the first stories told under the night sky to the equations written on chalkboards. We have sought to understand our place in the cosmos. That impulse has carried us from myths to mathematics, from Earth-centered heavens to galaxies without end, from certainties to questions. It is the same impulse that drives the search for other universes and for deeper laws. The final lesson of this journey is not that we are insignificant, nor that the universe is incomprehensible. It is that reality is richer than any single perspective can capture, and that our role is to keep asking, keep probing, keep expanding the horizon of what is known. The laws of physics may be contingent, the constants may differ elsewhere, the universe may be one among many. None of this diminishes the beauty of what we have discovered. It magnifies it, showing that our knowledge is a fragile but luminous flame in a vast and mysterious night. Science thrives on humility. To admit what we do not know is to open the door to discovery. To question what we thought eternal is to invite deeper truths, whether the path leads to a final law or to an infinite regress, to a single universe or to a multiverse of possibilities. The pursuit itself is what matters. Each experiment, each theory, each observation is a step in the unfolding dialogue between humanity and the cosmos. Perhaps the deepest act of humility is to accept that the universe does not need us, but that we can still find meaning in understanding it. The stars would shine without our gaze. The galaxies would swirl without our awareness. The constants would hold their values without our equations. And yet, through the accident of being here, we have become observers, storytellers, seekers of order. In learning the laws of nature, contingent though they may be, we have learned something of ourselves. The closing thought, then, is simple. Our universe may be one of many, or it may stand alone. The laws of physics may be necessary, or they may be contingent. The constants may be eternal, or they may vary beyond our reach. We do not yet know. But in the act of questioning, of searching, of embracing both knowledge and mystery, we step into the vastness with humility. And that humility is itself a kind of wisdom, the recognition that reality is always greater than our grasp, and that the quest to understand it is endless and endlessly worth pursuing.